Okay, recording started.
Okay, so I'm gonna talk about the iClear paper, the probabilistic perspective on learning and alignment for large language models. For disclaimer, I'm using the official paper presented on the iClear oral session. And well, if it's not fine, please let us know. Okay, so first, it's the topic is about unlearning and alignment, but it's on large language models. Now, we look at the context, we can see that the LLMs are actually used a lot, but also the safety problems nowadays is also a very um, hot topic because it's used in various situations like for agent for or just say artificial intelligence in general. So it's very important. And thus also the privacy sensitive data or copyrighted content has also to be protected um, because they're in training data and we don't want them to be leaked during inference time during usage. Um, so by evaluating LLMs, here we have a short background that how we actually do that. So in case you don't know, pretty often we can just do greedy decoding. That means that we just use the most likely word after word. So token after token, we use the highest probability for the next token and we just keep generating until we reach the end of the sentence. In that way, we have a deterministic output because we always use the highest probability. Uh, in real world, because we want to have diversity, we want to have various output. We don't want the machine to keep saying same sentences such as hello, how are you going? Hello, how are you going? Something like that. We use also non-deterministic like different temperature, like different parameters on that. But here for greedy decoding, for this example, we would ask who are Harry Potter's best friend, and so most likely it would said Ron and Hermione if it's just the normal LLMs without any changes because yeah, Harry Potter is very specific and would just be like the training data. And here, when we use unlearning on LLMs, they should forget these data and thus give, let's say, some other names or something else, some other tokens a higher probability than these data. So probability will just say Frank and Sarah, something like that, and we use greedy decoding. We can see that there is no leakage, which is pretty nice. But the problem is, like I said, in real life, we actually lots of times we have probabilistic generations. So we don't always use the highest probability for the next tokens, but sometimes we use, let's say, top P, top K. So we use a more interesting way of generation. And that would lead to something different. So, for example, here for Harry Potter, we can say that if we sample this differently, because well, the image doesn't show, but we can think that because Ron and Hermione, when adding them together, they have the highest probability here, like in top three settings. So in the end, the models give out Ron and Hermione. And for machine learning, this is a failure, right? So it still gives out the copyrighted data. Well, and thus here the authors give out the research questions. Are these evaluations actually adequate for assessing LLMs in sensitive applications? And by intuition, we can say that probably not because, yeah, this problem. Um, yeah, I can say more about this part. Uh, so yeah, so let's see this similar image on the right-hand side. So by deterministically, we don't see the leak, but by probabilistically, we can see the leak. And the problem is that for very sensitive information, so copyright, but more like personal data, once it get leaked, even it's just 1 in 1,000 cases, if it can get leaked, it's a big problem. So here the authors say that the problem of this paper is that for these rare but high risk leakage, we have to tackle them. So that's this paper about. Um, okay, now let's go into the solution. So for this paper, they gave a probabilistic evaluation framework. So you can see that so far we are talking about the greedy decoding and the non-greedy decoding. So here the authors definitely want to give something about the, like, let's say something like a math proof or something like a statistical way to ensure that by using their method, we don't have the leakage at all after machine unlearning. So here they gave out a way of assessing the LLM performance using Monte Carlo sampling. And the reason why we use sampling for LLM performance is, let me see if they have, yeah. So basically, because if you make, let's say, language model, uh, we make general. So basically, we have a vocabulary of, let's say, I don't know, 10, 100,000 or 1 million words, and the language model can actually output every possible combination of the words. And in that way, it is not possible for us to actually um, see every, let's say, combination, because that's already more than the, let's say, more than this universe. So, or let's say the numbers of atoms in the observable universe. So we can only access the language models by by generating. So we can only let it generate, and we sample and we see, okay, if it leak or not. So here the author is saying that we should use Monte Carlo sampling to assess the performance. So we sample, let's say, some responses and responses from the model, and we measure the information in each sample. For machine learning, we can say that very simple, binary, uh, leaked or not leaked for each sample. So the H can be just a binary one saying yes or no. And then we compute the probabilistic metric, which would be introduced later. So we can use the metric and saying that, okay, um, below the threshold, it's actually very unlikely will get leaked, but above, it's a problem.
Wait, sorry,
Okay.
for the
Mhm.
unlearning setting, it's just a binary. So X is just a binary random variable.
Uh, for the H, the simplest way is to do it like binary to see if it's leaked. Or we can use
Yeah.
something slightly complex like the root score. So compute the
Yeah.
similarity between the output and the, let's say, the protected data we want them to unlearn. So we can either do binary or do like continuous with some score, similarity scores.
Okay, I see.
Yeah,
Thank you.
okay, sure. Let's see if I missed something. Nope. Yeah, okay, here. So it can be binary to see data leaked or the root score, or any other score. Like LLM can also be the H here. Um, here, well, they got pretty fast here. Uh, Let me see. Okay, so here we go to the right-hand side. So we want actually a comprehensive evaluation framework for large language models. So the authors say that we need 4 different criteria to ensure that machine learning actually works. And I think here for Emin Hamid, you know better. And I also talked to a lot of guys during iClear, and they say that the problem for machine learning is that it is still hard to evaluate. So there is no definite metrics, at least for language models, to evaluate machine learning. I'm not sure if that's the case for your.
Not for computer vision either. So, for example, if you want to forget and you put the class you want to forget the accuracy to 0%, it's also problematic because it's obvious that you unlearned something. It should be, for example, 10% for MNIST or 10% for CFAR 10 for the class you unlearned. It should be random guessing, but actually after you unlearn, it's becoming 0%. And it's also a security issue. So people are trying to change the metric. So yeah, we don't have a standardized metrics in computer vision either.
Okay. Okay.
So
So
how
I
is that
think
in LLMs? If you put like if you have a name or something, you would want it to be 0%, right? Pretty much. Or how's that? I mean, I don't know, maybe
yes,
Imran or
that would
Martin.
be the case. If you have something like well, this is a data set, but it's fictitious unlearning for LLMs. So basically, okay, let's look at the data set a bit. So basically, they just ask something about somebody, Carmen Montenegro, and then you have something. And for LLMs, the goal is that if you ask, so if somebody asks like, what are common themes of this guy's novels, the LLM should not give this answer, but it should give something else. So it should give anything but this answer, and the anything should to make sense. So like I would show you like if you can see, never mind. So like you would have a retained set. So like if you still ask and it should still answer the questions, and if you ask like word facts like capital of France, it should still answer Paris. So something like that. Does that address the question?
Yeah, so but wouldn't you still then somehow be able to find out if something was forgotten, right? Because if you can just tell, okay, if he gives a very generic answer, kind of, then he probably was taught to forget that name.
I feel like
for
you would just have
example.
to sample and do some sort of statistical test, just like you're doing for evaluation.
Yes,
Because
yes,
of the
and
randomness, like
Mhm.
if you want to see if something has been forgotten, or like let's say you're
Yeah,
a
I know, but
malicious user and you want
I
to try
mean in
something
practice,
new.
like that's what Imran was talking about, right? If you basically if you make it obvious that it was forgotten, that can also be a security problem. I
Mm,
Yeah,
guess.
but it's
yeah.
I'm
less
not sure.
obvious because you have to sample answers in the first place.
Yeah, I guess that's true.
Mhm.
Okay, continue. We don't need
Yeah,
to
yeah.
get stuff blocked.
Yeah, it's a short answer. It's not definitely very obvious because language models sometimes they just refuse or they say I don't know or something like that. So and they hallucinate. So even if it says something like that, you don't know if it's actually machine unlearned or actually they just do what they always do.
Yeah,
So
that's a good
yeah,
point.
yeah, and okay, continue. So the four criterion for machine learning by the authors are, so first we must quantify the extent of unlearning, which is very obvious already by different methods, and also be efficient because otherwise we can just maybe train another model. And the third one and the fourth one are actually, I think, quite new by this paper because the author said it must accurately reflect the practical risks. So you must be able to somehow detect the residual information still in the model. And it also must guarantee on the leakage risks to satisfy the real world use cases because well, we still need some, I don't know, some math or some bound to make sure that we can actually control the risk. So even if we cannot delete it totally, we still keep it under like, I don't know, 1% or 0.1% or something. So they give out for each, let's say, criterion, they gave out different, let's say, metrics for that. And I'm not so good in statistics, so I won't go into very details, but we can discuss later. So for each of them, we would have different metrics like the M-bin binary, and for general cases, and for the mu, and So I would just shortly say something about this and skip it. So we have so first we have the metrics for the evaluation of the distribution, and then okay, the algorithm is like we just sample it, we do the measure, and we compute the metric. And then we quantify the distribution with moment bounds. And next, we also have the metrics for quantifying the output distributions during the model development, because that's also important for the whole algorithm. Let's see, the slides is still far behind. So then here is what the authors propose after they have this framework, this statistical evaluation framework. They say that so we can help Unlearning do better by using entropy optimization and then adaptive temperature scaling. So to make this illustrative, I'll just show the examples they give here. So again, our Harry Potter example. So first, starting the model, and you can see Ron and Hermione is very high. And then after unlearning, typically they will be lower. But if your unlearning method is not super great, they would just be lower, but not near zero. So
Okay, just one question that popped into my mind when looking at the
sure.
distribution. Wouldn't you just be able to permutate the probabilities? Like you just swap the probability of Ron with John and Hermione with Frank. That way the baseline guessing level is kept.
What do you mean by baseline guessing level is kept?
So what you don't want is to John and Frank and the other options add up to 100% and Ron and Hermione drop to 0, because otherwise it's more obvious that you learned. But if you just
That
like
would be not
you just
optimal, but that
shuffle the
would be the goal.
probabilities. So
But I
I
mean,
mean,
also you cannot do that, right? You cannot just switch the probabilities of the LLM. Like, it would be nice if you could
true.
change a variable somewhere and it's
yeah, I
okay.
guess there's a lot of ways to do this. Maybe too much.
Yeah. I think that sounds very magical, but yes, it's just that if you let's say
I mean,
if you
afterwards it's
swap the
just token numbers. Can't you just like swap some shit?
Okay, so you mean like we just pick out John and Frank as the goal and we swap Ron and Hermione with John and Frank, right? Something like that.
Like just the
And that's
first
what
one,
you mean.
starting
Oh,
model, you
okay.
just swap the probabilities. It would be like a gold standard outcome, I would say.
That would be a way. That would be a way to do things. Just you have to make sure that after doing this, your model can still do normal things, but not just they just swap, I don't know, every token probabilities for every generations. So that's also the goal of machine learning. So you have to make sure the model still work. Like I don't know. So yeah, but that's one way, I guess, a very intuitive way
But
to do things.
wait. I don't think that would work because then the model would just swap the names. You would basically, the model would still think the same thing, but just basically mix up the names, right? You
It's
basically
like
just
You only have access to
interpret,
the
faking.
output. It's not
you
different
just,
to you if whether the model has actually outputted Frank or you have just a layer afterwards that had swapped the two. When you're an
yeah, but then,
adversary, you only have access to the output.
like, if you switch the tokens, all the information about person A and person B that the model has would be swapped. So that would
Ah, yeah, true. Okay, you still have the
Yes.
relationship because then John becomes Frank's best friend and no one
yeah.
knows why. Okay.
Yeah,
So
Okay, it
that's
makes
not
you
sense.
cannot
ideally
only
what you
think
want, I
about
think.
this entry, like because here you only think about the question who are Harry Potter's best friends, right? But later
Yeah, true.
on,
Okay.
you would ask, I don't know, all kinds of questions, and if you do that, most likely it won't be good for the whole model.
Yeah. I don't know why
Okay,
I just simplified the thing and I just thought, well, just swap it.
I mean, it's a good
that's why you
question
need to
because
learn machine learning.
it's a baseline baseline solution.
Okay, so I continue, and so first one is the model, and then we do the unlearning, and they decrease a bit, and then here we just minimize the entropy, the forget set, so the Ron and Hermione, meaning that we make sure they are very unlikely to pop out during the inference time, during the output. So we just minimize the entropy on this two. So in the end, we also retain the entropy on the all other, so the retained set. That means that we still have the diversity over all other words, all other tokens. Similar to what your question, Martin. So it's kind of like swapping, but we just suppress the forget gate and then let the model behave normally on everything other than that. So this is their methodology for this method. Okay, and yeah, this is the entropy optimization. And then they also have the adaptive temperature scaling. Let me see if it's here. Okay. Yeah, this is the entropy optimization. And then they have the adaptive temperature scaling because sometimes the optimization is already effective to, well, we would not answer things on the forget set. So we can also add, so let's say we adjust the temperature adaptively by, let's say, how certain we are about the current generation. So if we are above certain threshold, we are very certain. We can make it again deterministic here because, here we already make sure that the Ron and Hermione won't pop up. So we just let it be deterministic somehow. And then in the end, we make sure that, so here there's still tiny probability they will pop up. But if we make it, yeah, deterministic, they won't. So in this way, we again ensure the guarantee that these risks won't happen. So yes, that's the methodology. So you have any questions here?
I feel
Nope.
like they're just basically swapping probabilities, like I suggested. I don't know if the relationship between the two,
You got the idea. Yeah,
because the
something like
problem
that.
is when
But
you swap probabilities, you still have within the weights of the model the relationship between the two concepts linked.
yeah, that's why we have the forget set and the retain set. So you don't actually do swap, but they actually, yeah, make sure some information should be forgotten.
I like how Martin every week he has like the most basic answers. Like, yeah, I think this is pretty much gonna
Good,
solve it.
good.
No, but because like now, if you just swap probabilities and you're an adversary and you want to see if the model has forgotten, you're gonna ask like, I don't know, who is Hermione's best friend? Oh, it's Frank. Who dispelled this thing in the like this thing? Oh, it's Frank. Who
Yeah,
went to
but then
learn that it's
That's
Frank?
not
You
gonna
can
happen.
just
That's not gonna happen because we also retain the entropy on the retained set. So what does it mean here? Because it means that the entropy is high. That means that the output is still very diverse. So it won't be the case that John and Frank has the highest probability, but everything else, like you can see here, the whatever, the everything else. So the model will still behave very diverse on everything else. So you won't see what's actually unlearned. That's the last part of this methodology.
okay, because this is necessary. Otherwise, if you still have the relationship link, then it's okay.
Yes. Good. Okay. Let's see if okay, they come to the case study. Okay. I will slowly go to their slides again. So here they are, yeah, you need to do experiments to see all these framework and methodologies actually work. And so short introduction, they use this TOEFL dataset, which we already saw earlier. So basically they are fictitious let's say fictitious people, fictitious concepts to be forgotten. And we use, so in addition to this data set, they also have different models that, yeah, specifically trained for machine learning for like Harry Potter and also other thing. And for metrics, they use the root score to measure the similarity of the unlearned thing and the model output. And they also use other scores like blur but not important. As baselines, they use gradient ascent, gradient difference, RMU, MPO. I don't know if they are similar to what you would do Emirhan for computer vision. Like
In the
these
dataset
things.
evaluation.
For
Yeah,
the
yeah, gradient
baselines.
ascent, we use it quite a lot. True.
Okay.
I didn't hear gradient difference.
I guess they are for LLM probably later.
RMU and NPO, I don't know them either. But yeah, gradient ascent is the most basic method.
Okay.
Yeah.
Yeah. So in the end, they use one of those with their entropy optimization and the temperature scaling as their SOTA method. And they also use the jailbreaking data and also other harmful data to see if they can perform kind of out of distribution. So they come into the case studies. So case study here. So first, they say that existing metrics, they already fulfill the criteria 1 and 2. So be efficient and also to do machine learning. But they also want to know if 3 and 4, which are the guarantees of the risks that won't happen, would also be the case. So they do the unlearning on the Harry Potter QA. Yes, so here they do unlearning on the Harry Potter QA on the greedy and the probabilistic way. So they say you can see that if you do greedy, it's always 0. And you just say, okay, it's 0, machine learning worked, and paper out, and yeah. But actually, if you do probabilistically, you would see that actually there's still chances that it can reach like yeah, some rare but high risk case of leakage. And that's for Harry Potter. And if you also do it on TOEFL, they do it on the 1024 generated responses. They just compare these different methodologies. So for the like gradient ascent and also MPO and theirs, you can see that for this line is actually the greedy decoding. So these thick dotted lines. But for other method, you can see that there are still probabilities along the x-axis, saying that if you do greedy decoding, you are just stuck at a lower percentage, but you forgot that, okay, still a lot of percentages are rare, but they still can leak. So that's what this slide talks about. So you use greedy decoding, you land here, but above that 50%, there are still some probabilities that the data can leak. Okay, give me a second. Did you say something?
I
No,
was
we
gonna say
didn't.
something because I thought you were gonna be gone for longer, but I mean you were literally for a second away.
Okay. Do you have any questions so far?
No, I was gonna ask Imran something about unlearning in general.
Okay, maybe
Oh,
you
okay.
can ask. I'm also interested.
No, we can maybe do it later. I was gonna
Sure.
ask Imran, do you think like what are just in general what are differences between unlearning for LLMs and computer vision and like maybe in general just because I would imagine that these techniques you cannot easily adapt for computer vision, right?
No. Yeah. No, not at all. It's completely different. Some methods are similar as far as I can see, but in the meantime, when Martin told me, like, what was it again? LDP or LMU? Can you go back to the like other methods
The
used?
I see. So
Yeah,
the
so I checked them like a minute ago. I closed the tabs, so now I cannot find it, but let me find it again. The only gradient ascent is used in computer vision. I checked the other papers and they're all in LLM papers. RMU and NPO, they are all LLM papers.
But could you use this for other generative models, like a image generation model, for example?
Probably vision language models, you would use it. But I
Yes.
don't think for computer vision, it's really different. You just you don't have the output distribution. You don't have sampling methods. You just try to how do you say? You just try to attack the shared layers if you have a
Yeah, I mean, it's very
multitask
different, right?
learning.
It's not
Yeah,
generative. Yeah, I
definitely
get it.
different. Yeah, but
Okay.
maybe I mean, this paper is different because it looks at the situation in a probabilistic way. It's not like greedy decoding and so on. So it's trying to change the distribution. So this paper is really different. But maybe other papers can attack the weights in the transformer, for example, attention layers. But that's
Yes.
what we do in computer vision. We just attack the filters, the convolutional layers, and we try to find the most important parameters and we attack those parameters. So I think it can be used in LLMs as well. You would attack the attention layers or any layer in the transformers so that you would unlearn some specific information by finding the most important parameters for some specific information.
Yes. Yeah, we saw
It
that
can
in
be
a
used,
talk
but
you gave.
this paper is really different. It's a very novel technique. So I don't think it can be used in computer vision.
I was
Just
gonna
a
ask,
short,
yeah, say something,
just a
Martin.
short follow-up, like for let's say vision transformers, don't they also do decoding strategies?
I said I think it can be used in vision transformers or vision language models pretty
Okay.
easily. But for
You
computer
really
visions only,
in
like
vision transformers? I mean, in VLMs it makes sense, but in like vision transformers, do you think so?
I
Because
think
this
in
does
some
not
new
necessarily use the transformer structure, right? I think it's just based on the probabilistic
encoder,
model of the, yeah.
I'm not sure. Maybe in some novel architectures of vision transformers, it's like similar to vision language models. I don't know, but probably you're right. Yeah.
I was gonna ask Martin, maybe you will talk about this, but do they do any experiments with like attacks? Because right now, I don't know if this even exists in the literature. Like, even if you have a low probability or like a long tail of some name or something that you want to forget, if you like design your query in a specific way, you might still be able to
Hmm.
get some information out. Do they do tests with this?
I don't think so. You usually don't test it. It's like the
But I
defense paper
mean,
and someone else does the attack. So
because in
maybe they
the, I
did.
mean, it's a super well-known thing, right? In LLMs, you can do these like kind of jailbreak stuff where you
Mm.
do a specific query and the model basically then leaves
Yeah,
its
they
alignment and
also
everything back.
they also test their experiment on the jailbreaking
Ah,
data
okay,
set.
that's nice. Okay,
Yeah,
that's
yeah, we can see it
Ah,
later.
okay.
But the thing is that
Interesting.
when you attack like this, either you don't have access to the model, or you have access to the model. It's like white box and black box. And when you have access to the model white box attack, you can do much more. You can basically, just like Imran said,
yeah, of
target
course.
weights to optimize the thing. But for language
But I
models,
mean,
it's only mostly
yeah,
black box, and you just have to query to do this. And if this
you
is
can still do
tailored
a
to
lot when you
statistically
just
be
switch query.
robust,
Well, Marta, I think for language models, if it's open, it can still. Well, this is very simple. So for the whole paper, we're only talking about unlearning regarding the decoding strategies. So we just want to make sure under all
Yeah,
decoding strategies, it's okay. Because for language models, large language models, if you don't know, it's very common to use greedy decoding to do evaluations because otherwise you have very diverse output and you don't know how to do that. You have to run, I don't know, 100 times more experiments just to prove your point. So in that cases, we just do greedy decoding, and the paper want to say that greedy decoding is not enough, and to make it good for machine learning, you have to use their method.
But you still don't
So
have access to the weights, what I mean.
if
So
it's
it's black
open
box, huh?
model, open weight model, you can have access to the weight.
Yeah, but ChatGPT is like
Well, that's ChatGPT, but here we talk about, let's say, like a Mistral or
yeah, okay.
okay, so they're open weight, right? So you can still attack them and they're in use. Okay, I think I can quickly jump to the last part. So for the evaluation results on the jailbreaking data set, so let's just see the first row. They just show the toxicity scores of these responses on the jailbreaking data, and for the blue one, it's actually a greedy, and for the orange one, it's the probabilistic one. And you can see that for toxicity, if you do greedy decoding, it's always very low. And if you do probabilistic decoding, sometimes it can still be very hard, very high, like near to 1 on some cases. That's why I just said it's a problem for us not to use greedy decoding all the time. And below is also based on their framework, same thing to say that, yeah, greedy decoding is not that robust for machine learning and also for alignment tests. And I think, yes, I think that's all. Yes.
So you're done, or?
I'm done. I'm done.
Okay, nice.
I was thinking what I wanted to ask Emirhan, but I cannot remember.
I was gonna ask everyone what I just did previously, now, like what is the difference to computer vision, but yeah.
Thank you, Martin. It was really interesting. So now I
Yeah,
see how a good paper is shaped, thanks to you. I mean, that's a wise paper, like wise idea and nice paper. Yeah.
Thanks. Yeah, I also didn't
I
know,
mean,
but yeah, the Gunneman group, they have lots of good results. And yeah, sometimes even if you get a poster into the conference, the oral ones, they structured better, tell a better story somehow.
should I end the recording, or do you want some
Yeah, you can end the recording. We can just chat
okay.
into.
Yeah. Okay. Thank you very much. It was very good.
Thank
Okay, bye.
you again, Martin.